So imagine you're sitting there just staring at your own reflection in a Zoom waiting room.
Oh yeah, the worst feeling.
Right. The camera light flicks on. Your palms are, probably a little sweaty.
Definitely sweaty.
Because you are about to enter an interview that could literally land you a $500,000 compensation package. We're talking at a FAANG company. So Google, Amazon, Meta, or, one of the tier 1 product giants.
Yeah, the stakes are just immense.
Exactly. And the role is DevOps, or Site Reliability Engineer, SRE. The person on the other end of that call, they are not going to just ask you to define a few basic acronyms or write some simple Python script.
No, absolutely not. They are preparing to throw you straight into a live production fire.
Which is terrifying. But today, on this deep dive, we actually possess the literal answer key.
It's pretty incredible that we got our hands on this.
It really is. It's a highly confidential 60-minute internal simulation playbook. It's used by senior technical interviewers to evaluate candidates across all levels. So we're talking mid-level engineers all the way up to staff and principal architects.
Yeah, and this document, it's essentially the ultimate grading rubric for modern systems thinking. I mean, it completely strips away the theory.
Right.
And it focuses entirely on how you operate when millions of dollars are on the line, like when the database is locked and the incident response channel is just flooded with panic.
Which is when you really see what someone is made of.
Exactly. The playbook is designed to separate the mechanics, the people who just know how to type commands into a terminal, from the true system architects who actually understand the blast radius of those commands.
The blast radius. I love that term. So let's just jump right into the structure of this gauntlet.
Let's do it.
Because before any code is even shared, the playbook dictates a 5-minute phase called cultural and communication alignment.
Sounds very corporate.
It does, right? That sounds like an icebreaker. But reading through the interviewer's hidden intent here, it is heavily weaponized.
No, completely. It's a trap right out of the gate.
Yeah, because the very first question the interviewer asks, walk me through your journey. What does a great day look like for you?
Such a classic question.
Right. But if I'm sitting in that chair and I know I'm interviewing for a highly technical cloud infrastructure role, my instinct is to lean super heavily into the tech stack.
Which is what almost everyone does.
Exactly. I would probably say something like, a great day is when I get to refactor a massive, messy infrastructure into clean, modular Terraform code.
Yeah.
Or, when I can fully automate a complex Kubernetes deployment pipeline so my team never has to touch it.
You're trying to show off your chops.
Yeah, I want to show them I am a master of the tools.
Which is exactly why the playbook classifies that response as a glaring red flag.
Wait, really? A red flag?
Oh, absolutely. Particularly for senior and staff level candidates. See, the interviewer is running a background process here.
Okay, what are they filtering for?
They're filtering specifically for your focus on business impact versus your focus on tools.
Okay.
When you say your best day is writing elegant Terraform, you're telling the interviewer that you are entirely focused on the hammer, not the actual house you're building.
You're missing the forest for the trees.
Exactly. You lack the broader business context. The green flag answer, the response that instantly puts you in the strong hire track, sounds entirely different.
So what does a strong candidate say?
They say something like, I moved from backend development to SRE because I want to take ownership of systemic reliability. A great day for me is when I identify a bottleneck and reduce our P99 API latency by 40%, directly improving the checkout experience for the end user. Wow.
Okay, so you're speaking the language of outcomes, not inputs.
Right. You're quantifying the value you brought to the actual business.
Rather than just listing the open source projects you enjoy tinkering with. That makes so much sense.
Yeah, they want business partners, not just coders.
Okay, so then the playbook moves to a depth probe. It asks what I like to call the sleep question.
Oh, this is a great one.
The interviewer asks, what is the most complex infrastructure you've owned and what kept you up at night?
Yeah, that really gets to the core of it.
It reminds me, honestly, it's like talking to commercial airline pilots, right?
Okay, how so?
Well, a rookie pilot, they worry about memorizing the instrument panel. They're just hoping they don't hit the wrong switch.
Sure.
But a veteran pilot with like 10,000 hours, they don't even think about the buttons anymore. They worry about invisible structural fatigue or air traffic control miscommunications or macro weather patterns.
That structural fatigue analogy is absolutely spot on because asking what keeps you up at night is a direct test of your operational maturity.
Right.
If your answer is, I worry about our primary Jenkins server running out of disk space and halting our deployment pipeline, you're signaling a very localized junior scope of
You're
experience.
still worrying about the buttons.
Exactly. The interviewer's rubric expects a senior candidate to say, I own the compute platform for 200 microservices across 3 geographic regions.
Wow. Okay, scaling way up.
Right. And then they say, what kept me up at night was the latency overhead in our cross-region database replication and the risk of a split-brain scenario if our primary region's control plane went dark.
So you are demonstrating that you worry about systemic architectural vulnerabilities.
Yeah.
Things that threaten the entire enterprise.
Precisely. It's about scale and blast radius.
Okay, and right in this initial alignment phase, there's another trap. The interviewer demands the candidates draw a clear philosophical boundary between two terms the industry loves to blur, DevOps and SRE.
Oh yeah, the classic debate.
Now, I'll play the skeptic here for a second. In most startups and mid-sized companies, those are just two different titles for the exact same job, right?
That's definitely how the market treats them, yeah.
I mean, it's just the person who writes the CI/CD pipelines and fixes the servers when they crash. Is there really a hard boundary?
Well, the playbook treats conflating the two as an automatic failure for the system's architecture portion.
An automatic failure, just for mixing up the terms.
Yep. To pass this section, you have to articulate the boundary. DevOps is fundamentally a cultural movement.
Oh.
It's a philosophy of shared delivery, right? It's about breaking down the traditional silos between software developers who write the code and operations teams who deploy it.
So it's a way of working together.
Exactly. Site reliability engineering, SRE, on the other hand, is a highly specific prescriptive discipline. It was invented largely by Google.
Right. The Google SRE book is like the Bible for this.
Yeah. And the definition the interviewer is looking for is this. SRE is the application of software engineering principles to operations problems, specifically governed by quantified reliability mathematics.
Quantified reliability mathematics. That sounds intense.
It means SREs don't just build pipelines. They use software to eliminate toil, and they enforce error budgets.
Okay.
If DevOps is the philosophy, SRE is the physical implementation of that philosophy using code.
That sets a really clear baseline. Okay, so once the interviewer verifies you understand the landscape, we enter the 10-minute concept validation round.
This is where it starts to get tricky.
Yeah, the playbook is explicit that this is not a vocabulary test. It is a stress test of your underlying assumptions.
Right.
Let's look at the error budget question. Everyone in this space knows the basic definitions, right? An SLI, the service level indicator, is the actual real-time measurement like your HTTP request success rate.
Yep. Raw data.
Right. And then the SLO, the service level objective, is your internal target, like aiming for 99.9% uptime.
Exactly.
And the SLA, the service level agreement, is the legal contractual promise you make to your paying customers, which usually has financial penalties attached.
Big financial penalties.
Yeah. So the error budget is just the inverse of your SLO. If your goal is 99.9%, your error budget is that remaining 0.1% allowance for failure.
Perfect breakdown.
So the interviewer asks, what happens when your team exhausts its error budget for the month?
This is a great behavioral trap disguised as a technical question.
Right, because in a high-growth product company, the product managers are constantly pushing for new features.
Always. Ship it yesterday.
Exactly. So if I hit my error budget, say the app is down for 43 minutes this month, I assume we prioritize stability, but we still have to ship the roadmap. We just, try to be more careful.
If you say that, you fail the scenario.
Wait, really? Fail it entirely?
Yes, because the SRE model relies on the mathematical enforcement of priorities. When the error budget is completely exhausted, the consequence must be absolute. Deployments freeze.
Completely. Even if the VP of product is screaming for a new release.
Completely. All non-critical feature releases are gated. The entire engineering team's effort is forcefully redirected toward reliability initiatives.
So like fixing technical debt.
Exactly. Fixing tech debt, improving test coverage, or optimizing database queries until the error budget window resets or recovers.
Wow.
If there is no consequence for breaching the budget, then the SLO is just a vanity metric. It means nothing.
It's just a number on a dashboard. Okay, so then the interviewer will follow up with a trap variation.
They always have a follow-up.
They ask, can an internal SLO exceed the external SLA? Meaning, can my internal target be stricter than my legal contract?
And what would you say?
I would argue it has to be, otherwise you are playing with fire.
You are correct. Your internal SLO must act as a buffer.
Okay, makes sense.
Because if your contract promises 99% uptime to the customer, your internal goal should be, say, 99.9%.
Right.
If you align your SLO perfectly with your SLA, the moment your internal dashboard turns red, you are already violating a legal contract and bleeding revenue.
Oh, that's a nightmare.
Yeah, the delta between the two is your operational safety net.
I love that. The delta is the safety net. Let's move to a concept that plagues literally anyone who has ever touched Kubernetes.
I think I know what's coming.
The dreaded CrashLoopBackOff.
There it is.
The interviewer asks, what happens when a pod goes into CrashLoopBackOff, and how do you diagnose it?
Standard question.
Yeah, the baseline diagnostic commands are fairly standard. You run kubectl describe pod to check for scheduling issues or failed probes.
Yep.
And you run kubectl logs previous to see the standard output of the container right before it died. But then the interviewer follows up with a psychological trap.
This is where it gets interesting.
They ask, is CrashLoopBackOff a bug in the Kubernetes orchestration system?
It's a very pointed way to phrase it.
It is. And my instinct is to say yes, or at least that it's an error state, indicating a failure in the orchestration layer to keep the application running.
And that's where people trip up. It feels like an error state because your application is broken. But from the perspective of the cluster architecture, it is a vital protection mechanism.
Protection mechanism? How so?
Well, imagine you deploy a container that lacks a critical environment variable. Or maybe it's trying to connect to a database that just doesn't exist.
Okay, so the code is fundamentally broken.
Right. The application code instantly panics and crashes upon startup. If the Kubernetes kubelet simply kept trying to restart that container immediately, like thousands of times per second, what happens?
Oh, I see. It would just be an endless loop.
Exactly. The constant initialization sequence would consume massive amounts of CPU cycles and memory overhead.
It would essentially become a self-inflicted denial of service attack on your own underlying physical server.
Precisely. It would drag down the entire node and potentially starve out all the healthy applications running alongside it.
Wow.
So the backoff mechanism introduces an exponential delay. It waits 10 seconds, then 20, then 40, capping out around 5 minutes.
So it's slowing down the bleeding.
Yeah. Is a Kubernetes actively defending the broader infrastructure from your broken application logic? Recognizing that distinction proves you understand the control plane's defensive posture.
That's a profound shift in perspective. It's not a bug, it's a shield. Okay, let's tackle deployments.
Let's do it.
The playbook asks the candidate to evaluate canary versus blue-green deployments.
A classic architectural debate.
So just to define them quickly, a canary deployment routes a tiny fraction of traffic, say 5% to the new version, monitors the error rates, and slowly scales it up.
Like a canary in a coal mine.
Exactly. Well, a blue-green deployment spins up a completely identical production environment alongside the current one. You have your live environment, blue, and your new environment, green.
Right.
You run your tests on green, and when you are confident, you reconfigure the load balancer to send 100% of traffic instantly from blue to green.
Flipping the switch.
Yeah. So the interviewer leans in and says, isn't blue-green always the safest method? If the green environment fails, you just flip the router switch back to blue, and you've mitigated the outage in seconds.
It sounds so appealing, doesn't it?
I mean, I have to agree with the interviewer here. From a pure infrastructure standpoint, having an untouched, perfectly functioning previous version waiting in the wings seems like the ultimate safety net.
Well, from a purely stateless compute perspective, your logic is totally sound.
Okay, I hear a but coming.
However, the interviewer is laying what the playbook calls the database coupling trap.
Database coupling trap. What is that?
Applications do not exist in a vacuum, right? They persist state.
True.
Let's assume your new code in the green environment requires dropping a column in the PostgreSQL database. Or, let's say, splitting a full name column into first name and last name.
A standard database migration.
Exactly. You apply that database schema migration, the green environment boots up, connects to the migrated database, and it works perfectly.
Okay, so far so good.
But then, a subtle application bug emerges under load, and you decide to trigger your safety net. You flip the load balancer switch back to the old blue environment.
Oh no. The old blue environment's code is still expecting the full name column to exist, but we just dropped it.
Precisely. The blue environment boots up, attempts a standard query, and the database throws a fatal error because the schema has changed. Your safety net is effectively destroyed.
That is brutal.
Yeah. By blindly trusting the blue-green rollback, you have caused a catastrophic system-wide schema conflict.
So blue-green is actually dangerous.
A senior architect must articulate that blue-green deployments are only safe if your database schema changes are strictly backward compatible across multiple release versions.
Which is really hard to do.
It requires incredibly disciplined, multi-phase data migrations. You can't just flip a switch if the state has mutated.
You cannot just look at the compute layer, you have to track the state. That is brilliant. Let's cover one more concept before the interview turns hostile.
Ah, yes! The hostility is coming.
The zero trust misconception. The interviewer asks, how do you implement zero trust networking in a cloud-native environment?
Buzzword bingo.
Right. So if I'm answering, I'd say, well, I build a highly hardened AWS virtual private cloud, a VPC.
Okay.
I establish strict perimeter for firewalls. I use private subnets for my databases without any public IP routing.
Sounds solid.
And I configure AWS security groups so nothing gets through the perimeter without going through a heavily monitored web application firewall.
That's zero trust, right?
I trust nothing outside the network.
You have just perfectly described perimeter security, which is the architectural antithesis of zero trust.
Wait, the antithesis.
Yeah.
The exact opposite.
Yes. What you described is the classic castle and moat model. You build a massive, heavily guarded wall around your infrastructure.
Right, which keeps the bad guys out.
Theoretically. But the fatal flaw in that model is that once an attacker crosses the moat, perhaps through a compromised VPN credential or maybe a supply chain vulnerability in a third-party library, they are inside the castle.
Oh, I see.
In a perimeter model, any application inside the VTC generally trusts any other application on that same internal network.
So if they break into one thing, they have access to everything.
Exactly. The attacker can move laterally. They can pivot from a low-level, unimportant analytics service directly into the payment processing database.
Because the database assumes, hey, you're inside the wall, you must be a friend.
Right. So what constitutes actual zero trust architecture?
Yeah, what is the right answer here?
Zero trust fundamentally assumes the network is already compromised.
Oh, wow.
It assumes the attacker is currently sitting inside your VPC. Therefore, the network location of a service grants it absolutely no privileges.
None at all.
None. To build this, the playbook looks for a candidate to describe an architecture where every single microservice interaction requires continuous cryptographic proof of identity.
Cryptographic proof, so like certificates.
Exactly.
Yeah.
You need mutual TLS/MTLS enforced by a service mesh proxy like Istio or Linkerd.
Okay, so how does that work in practice?
When the billing service wants to talk to the database, it doesn't just resolve an internal IP address. The billing service's sidecar proxy presents a short-lived cryptographic certificate to the database's proxy.
They're verifying each other.
Yes, they validate each other's identities, negotiate an encrypted tunnel, and only then is the traffic pass.
Wow.
Furthermore, you integrate identity frameworks like SPIF or Spire, so workloads are authenticated based on their cryptographic signatures, not their network addresses. And you use the Open Policy Agent to evaluate access rules dynamically on every single request.
That is incredibly dense.
Yeah.
It's like having a heavily armed security guard standing at the door of every single room inside the castle.
That's a great way to picture it.
And they are meticulously verifying passports every time someone wants to walk down the hallway, regardless of how they got into the building in the first place.
Exactly. It removes the network from the trust equation entirely.
Okay, well, we have survived the concept validation.
Barely.
Barely. But now, the playbook dramatically shifts the tone.
The gloves come off.
The interviewer stops asking definitions and essentially says, congratulations, you know your theory. Let's see how you handle a production fire.
Segment 3. The Crucible.
The Crucible, Part 1. This is a 25-minute stress test focused purely on incident response under massive financial and psychological pressure.
This is where you see who really has production experience.
So the interviewer lays out Scenario 1, the Black Friday outage.
The worst day of the year for e-commerce.
Here is the setup. You are the primary on-call engineer for a global e-commerce platform. It processes $2 million in daily transactions.
Big money.
It is 11:47 p.m. on Black Friday. PagerDuty fires. In the last 90 seconds, your checkout success rate has plummeted from 99.2% to 31%.
Ouch.
And every hour the system remains degraded, the company is hit with a $50,000 financial penalty based on vendor SLAs. You have Datadog for monitoring, and you are running a microservices architecture on Kubernetes in AWS.
Very standard modern stack.
The interviewer asks, walk me through your complete incident response. What is your first move?
Okay, so what would you do?
Because my immediate instinct, knowing we are bleeding $50,000 an hour, is rapid mitigation. I would log in, locate the checkout service, and immediately run a restart command on the pods. Or, if I see a deployment happen recently, I'm mashing the rollback button. Just put the fire out.
Which the playbook classifies as a level 1 junior mistake.
Really, a level 1 mistake. But the system is actively failing. Action is required right now.
Reactive guessing under pressure is how you turn a partial degradation into a catastrophic global outage.
Okay, explain that.
If you blindly restart the servers, you might temporarily clear a memory leak, sure, but you have fundamentally destroyed the state of the system.
Oh.
You just erase the forensic evidence of why the service broke. When the memory fills up again 10 minutes later, you are back to square one with zero data.
I didn't fix the disease, I just wiped away the symptoms.
Exactly. Furthermore, if you guess wrong and roll back a foundational authentication service instead of the checkout service, you could lock millions of users out of their accounts entirely.
Making it infinitely worse.
Top-tier organizations prioritize methodical isolation. Step 1 is not executing commands. It is establishing command and control.
Command and control, what does that actually look like?
You declare a high-severity piezo incident. You spin up a dedicated war room or Slack channel. You page the secondary on-call engineer and the incident commander to handle communication with stakeholders.
So you're managing the human element first.
Yes. And you freeze all state changes.
Okay, we established the communications framework. We aren't touching the code yet. So what is step 2?
Step 2 is structured triage. You need to establish the blast radius.
How do you do that?
You open your observability platform to check the service dependency map. You run targeted Kubernetes commands. The playbook specifically mentions running kubectl get pods field selector status.phase. Running.
Oh, well, that's clever.
Right. Instead of scrolling through thousands of healthy services, this command instantly filters the cluster state and isolates only the workloads that are currently failing.
It cuts through the noise.
Exactly. You check the AWS Application Load Balancer target group health metrics. You are actively diagnosing the layer of the failure. Is the application code crashing? Is the database transaction pool exhausted? Or has an underlying AWS availability zone gone offline?
You are diagnosing before you prescribe a treatment. Okay, let's say I follow that structured approach. I dig into the metrics, and I discover that the checkout service is timing out, specifically because a new version of the shipping calculation microservice was deployed 8 minutes ago, and it's introducing massive latency.
Okay, a bad deployment. Very common.
Right. So I confidently tell the interviewer, I found the root cause. I execute kubectl rollout undo deployment shipping service to revert to the previously known good state. I fixed it.
This is where the interviewer introduces the escalation curveball.
Oh.
They look at you and say, you execute the rollback command, the Kubernetes API accepts it, but the new pods refuse to spin up, the replica set is hanging, the outage is continuing, and the financial penalties are mounting. What is your next move?
Oh man, the panic definitely sets in here. If the orchestrator itself is failing to execute the rollback, I am stuck. Do I start manually deleting pods? Do I try to forcefully patch the deployment YAML in real time?
A mid-level engineer gets stuck fighting the Kubernetes control plane. A staff-level engineer recognizes that when the application orchestration layer fails, you must immediately abstract your solution up the stack to the infrastructure layer.
Abstract up the stack, meaning what?
You abandon the broken Kubernetes deployment entirely. You go to your AWS Application Load Balancer or your API Gateway, and you implement traffic shifting.
Ah.
You route all incoming checkout requests away from the failing cluster entirely. You direct them to a cold standby environment in another region. Or, if that isn't available, you route them to a static, degraded mode. We are experiencing a high-volume waiting page.
You mitigate the user impact at the network edge, entirely bypassing the broken application layer.
Exactly. You stop fighting the broken tool and you route around it.
That requires an incredible mental map of the entire architecture, not just the specific tool that broke.
It's the difference between knowing Kubernetes and knowing systems.
Let's look at another crucible scenario from the playbook, because this one's just a massive trap. Scenario 4, the security breach.
Oh, this one is brutal.
The setup is terrifying. Your AWS Cost Explorer dashboard triggers a billing alert. It shows an unexpected $47,000 spike in EC2 compute costs over the last 3 days.
Crypto mining, probably.
Right. Simultaneously, your security tooling flags unusual outbound API calls. You check the network flow logs and discover that 3 of your backend Kubernetes pods are making active outbound internet connections to an unknown foreign IP address on port 44444.
Port 4444. That is the default listening port for Metasploit, which is a prevalent command and control exploitation framework used by attackers.
Worst case scenario.
You have a confirmed active breach inside your perimeter. They have a reverse shell.
Exactly. And the prompt adds one final, crucial detail. Your cluster processes highly regulated payment card data. You are operating under strict PCI DSS compliance regulations.
The legal stakes just went through the roof.
The interviewer says, you have an active live security breach in a financially regulated environment. Walk me through your incident response.
So what's your play?
Now, knowing the Metasploit detail, the attacker has a reverse shell. They are actively inside the pods right now. The absolute, undeniable first priority is stopping the bleeding.
Okay.
I would immediately execute kubectl delete pod on the compromised workloads, or perhaps even terminate the underlying EC2 instances entirely just to sever the attacker's connection and stop the data exfiltration.
If you utter the words delete the pods, the interview is effectively over. You fail the scenario outright.
What? It is the biggest landmine in the entire document. But why? Why is neutralizing the active threat the wrong move? They are stealing credit card data.
Because you are no longer just dealing with a technical infrastructure problem, you have crossed into the realm of legal liability and digital forensics.
Digital forensics.
When you operate under PCI DSS or similar regulatory frameworks, a breach triggers mandatory compliance investigations. If you execute a delete command, Kubernetes will cleanly and instantly terminate that container.
Right, which stops the attacker.
Yes, but it also destroys the container's ephemeral file system, its running memory state, and its local log cache. You have just taken a flamethrower to a digital crime scene.
Oh my God. You've destroyed the evidence.
Exactly. By destroying the forensic evidence, you make it impossible to determine what the attacker actually accessed.
Oh, why is that so bad?
Because under strict compliance laws, if you cannot cryptographically prove what data the attacker did not touch, the regulatory bodies often force you to assume they compromised everything.
Everything. The entire database.
Yes. This triggers catastrophic public legal disclosures, massive regulatory fines, and basically irreparable brand damage.
Okay, the stakes are astronomical, but I still have an attacker actively exfiltrating data. How do I stop the attack without destroying the crime scene?
The playbook mandates a procedure of containment without destruction.
Containment without destruction. How?
First, you immediately isolate the workloads at the network layer. You apply a strict Kubernetes network policy targeting those specific compromised pods, configuring it to default deny all egress traffic. This severs the reverse shell connection and halts the exfiltration, but it leaves the pod running perfectly intact in its current state.
You essentially throw the pods into a network black hole.
Yes. They can't talk to anyone, but they are still alive. Next, you must capture the volatile state. You use a command like kubectl debug copy to forensic pod to take a live snapshot of the container's memory and file system for the security team to analyze.
Brilliant.
You also cordon the underlying physical node so Kubernetes doesn't schedule any new healthy workloads onto a potentially compromised server.
Quarantining the host.
Exactly. Finally, and crucially, you must lock down your audit trails. You ensure that your AWS CloudTrail logs and Kubernetes audit logs are being streamed to an immutable write-once, read-many storage bucket.
So the attacker cannot delete the logs to cover their tracks.
Right. You have to preserve the history of what they did.
You completely transition from an engineer to a crime scene investigator. It really highlights why the compensation for these roles is so high. You aren't just deploying code, you are managing existential legal risk for the corporation.
That's exactly what staff-level engineering is.
Now, the playbook notes that surviving these fires is only half the battle. Top-tier engineers are fundamentally hired to architect systems that don't catch fire in the first place.
Proactive versus reactive.
Right. Which brings us to segment 4, the Crucible Part 2, focusing on architecture, scaling, and migration.
This tests your ability to pivot from reactive firefighting to proactive strategic engineering.
The interviewer presents Scenario 3. The slow-motion crash.
Oh, these are agonizing.
You manage a SaaS platform with 2 million active users. You are 90 minutes away from your daily peak traffic hour. But the infrastructure is already redlining.
Not good.
The overall CPU utilization across the cluster is at 94%. Your Kubernetes cluster autoscaler is attempting to provision more servers from AWS, but it is failing.
Resource starvation.
First of all, your P99 latency, meaning the experience for the slowest 1% of your users, has spiked to an abysmal 8.2 seconds.
That's practically offline from a user perspective.
The interviewer sets the clock. You have 90 minutes to resolve a multi-layered scaling bottleneck before peak traffic triggers a cascading global outage. Walk me through your strategy.
This is a beautiful scenario because it forces the candidate to operate on two parallel tracks. You have to apply a tourniquet to the immediate bleeding while simultaneously diagnosing the root capacity failure.
Let's break down the expected solution. How do we apply the tourniquet?
You have to shed non-critical load to protect the core business functions.
Shed load, like turning things off.
Basically, a cluster at 94% CPU is suffocating. The candidate must articulate a strategy for identifying background asynchronous tasks.
What kind of tasks?
Perhaps massive analytics batch jobs, machine learning model training, or heavy database cron jobs. These are things consuming vital compute cycles, but are not in the critical path of live user requests.
Okay, so a user trying to check out doesn't care if the analytics job finishes right now.
Exactly. You leverage a Kubernetes construct called pod disruption budgets, and you cordon the nodes running those batch workloads, forcefully pausing them. You are throwing the cargo overboard to keep the ship from sinking.
That buys us a little breathing room,
Yeah.
but we still have the core issue. The autoscaler is failing to add capacity.
Right.
If I configure an autoscaler correctly, it should just ask the AWS API for more EC2 instances. Why would it fail?
Because the cloud is not an infinite magical resource.
It feels like it sometimes.
It does, but it's really just a collection of physical data centers. A very common real-world blocker is that an engineering team has hard-coded their autoscaler to request a highly specific hardware profile.
Like, I only want these exact servers.
Yeah, say the M5.2X large instance type. In a high-demand scenario, Amazon Web Services can and does run out of that specific hardware within a specific availability zone.
So Amazon just says, sorry, we don't have any left.
The API simply returns a capacity error. The architectural fix is to drastically diversify your compute requests.
How do you do that?
You must configure your autoscaler or implement a modern provisioner like Carpenter to accept a massive variety of instance families. M5, C5, R5, spot instances, varied sizes, so your cluster can aggressively consume whatever random capacity AWS currently has available.
You stop being picky and grab whatever hardware you can get.
Exactly.
The playbook mentions a deep cut here regarding that massive 8.2-second latency spike. It specifically asks the interviewer to probe the candidate's understanding of CPU limits versus CPU requests.
Oh, this is the separator. This separates the good from the great.
I understand the baseline definition, right?
Yeah.
A request is the minimum amount of CPU the orchestrator guarantees to a pod, and a limit is the absolute maximum ceiling it is allowed to consume. How does that relate to our latency crisis?
This touches on the underlying mechanics of the Linux kernel, specifically kick groups, and it is a major differentiator in the interview. I want to use a plumbing analogy here.
Okay, go for it.
Think of your CPU request as the guaranteed minimum water pipe diameter running into your apartment. You are always guaranteed that baseline flow. Think of the CPU limit not as a pipe size, but as a pressure valve managed by the building.
Okay, I follow.
In Kubernetes, if your application suddenly consumes too much memory, hitting its memory limit, the operating system executes an ohm kill out of memory kill. It forcefully assassinates the process. The pod dies and restarts.
Brutal but simple.
However, CPU is considered a compressible resource.
Compressible.
Yes. If your application suddenly requires massive processing power and hits its CPU limit, the kernel does not kill it. Instead, the pressure valve engages. The Linux kernel forcefully pinches the flow, artificially throttling the application's processing cycles.
So the application isn't dead, it's not crashing, it is just being brutally suffocated by the operating system.
Right.
Which is why a request that normally takes 500 milliseconds suddenly takes 8.2 seconds. The requests are queuing up behind the pinched valve.
Exactly. And the counterintuitive staff-level insight here is that when you are in a crisis state, trying to process a massive backlog of queued requests, you sometimes need to dynamically remove the CPU limits entirely.
Just take the limit off completely.
Yes. By removing the pressure valve, you allow the application to consume any unused CPU cycles remaining on the physical node, clearing the backlog efficiently rather than being artificially throttled.
That is a phenomenal mechanical breakdown.
It's all about understanding what the kernel is actually doing beneath your containers.
Let's look at the final crucible scenario. Scenario 5, the impossible migration.
This one gives people nightmares.
The setup. You have a massive monolithic legacy Ruby on Rails application. It is tethered to a single 3 terabyte PostgreSQL database.
A beast.
You have been tasked with architecting the migration of this entire monolith into a modern distributed microservices architecture. But the business requirement is non-negotiable. Zero downtime. No maintenance windows allowed. You cannot take the application offline for even 5 minutes at 2 a.m. on a Sunday.
Which is the reality for any global platform.
Yeah.
When you have users operating in every single time zone, there is no such thing as off hours.
True. But to me, this sounds like trying to replace the transmission of a car while it's driving down the highway at 80 miles an hour. How is this technically feasible?
It requires a masterclass in phased, decoupled architecture. The interviewer is listening specifically for a candidate to outline the strangler fig pattern.
The strangler fig,
Yeah.
like the parasitic plant.
Precisely. In rainforest ecosystems, a strangler fig seed germinates in the upper canopy of a host tree. It slowly grows its roots down the trunk, wrapping around the host.
Okay, kind of creepy, but go on.
Over years, the fig grows thicker and stronger, eventually entirely enveloping and suffocating the original tree, seamlessly taking its place in the canopy.
So how do we translate that botanical violence into software architecture?
Phase 1 is establishing the canopy. You deploy an intelligent API gateway directly in front of your legacy monolith. Initially, this gateway acts as a dumb proxy, routing 100% of user traffic straight to the old monolith.
So nothing changes for the user.
Exactly. Phase 2 is growing the first route. You build your first modern microservice, let's say the new checkout service.
Okay.
You configure the API gateway with a new rule. Route all requests for the checkout endpoint to the new microservice, but continue routing everything else to the legacy monolith. You are slowly wrapping the new architecture around the old.
But wait. Both the new microservice and the old monolith need to read and write to the database. And the prompt mandates that the new microservices must eventually have their own dedicated decoupled databases. You have a 3 terabyte state.
Yes.
If you can't turn the system off to copy the data, how do you handle the split state?
Database decomposition is the most complex aspect of this pattern. A strong candidate will outline the implementation of dual writes.
Dual writes.
You modify the application layer so that every time a user makes a purchase, the code writes that transaction to both the old monolithic database and the new microservice database simultaneously. This ensures all new data is synchronized.
Okay, but what about the 3 terabytes of historical data? You still need that.
You backfill it using logical replication. The candidate should mention a tool like Logical in PostgreSQL.
How did that work?
It hooks into the database's write-ahead log. It streams every single historical change to the new database asynchronously, catching it up to the present moment without locking the production tables.
So now we have the new service running and 2 databases perfectly in sync. Do we just flip the switch at the API gateway and go live?
Absolutely not. You introduce phase 3, dark launching, also known as shadow mode.
Shadow mode, that sounds cool.
It is cool. You configure the API gateway to duplicate incoming user traffic. It sends the real request to the legacy monolith, which serves the user, but it also silently mirrors that exact same request to the new microservice.
Oh, I see.
The new microservice processes the request and generates a response, but that response is discarded. It is never sent to the user.
You're running the new engine in production with real production data loads, but the user has no idea it exists.
Exactly. You do this to validate the logic. You set up monitoring to asynchronously compare the responses. If the new microservice consistently calculates the exact same checkout total as the legacy monolith, but does it 50 milliseconds faster, you have mathematically proven its safety.
Wow. And then,
finally, you initiate a canary cutover at the API gateway routing 1% of live traffic, then 10%, then 50%. Once the new service is handling 100% of traffic flawlessly for several weeks, you sever the connection to the monolith. The host tree is dead. The strangler fig has fully taken over. Zero downtime.
that is an incredible, highly choreographed technical ballet.
It really is. It takes months, sometimes years, to execute perfectly.
But the playbook notes that describing a pattern on a whiteboard is entirely different from executing it in the trenches.
Always.
The interviewer eventually stops the theoretical discussion and says, "Show me the code." We enter segment 5, live hands-on traps. You have 10 minutes to complete 3 live coding and configuration exercises.
People freeze up here.
It's not a test of your typing speed, though. It's an evaluation of your ability to spot production landmines buried in configuration syntax.
The devil is always in the details, particularly with infrastructure as code.
Exercise 2 asks the candidate to write a Terraform module to provision a highly available PostgreSQL database cluster on AWS RDS. The playbook specifically outlines the career-ending configuration omissions that candidates make when rushed.
Yeah, these are the silent killers.
One of the biggest flags is failing to include the specific line deletion protection true in the production database resource block.
It seems like a minor flag, but the blast radius is existential.
Really, just one line of code.
If you omit that line, a junior engineer in your team could run a Terraform destroy command to clean up a testing environment, accidentally target the production workspace, and the AWS API will happily and instantaneously obliterate your entire production database.
Oh, no.
Without a single confirmation prompt. Setting that flag to true forces an engineer to log into the AWS console and manually disable the protection before deletion can ever occur. It is an architectural seatbelt.
Another massive red flag is how candidates configure the database's security group, the firewall rules. When trying to quickly get the Terraform code to pass, a candidate will often hastily type 0.0.0000 into the ingress rules to ensure the database is reachable.
This is a classic, awful mistake.
Because what does 0.0.00 actually do?
By typing that, you are explicitly instructing the AWS firewall to allow inbound connection attempts from any IP address on the public internet.
The entire internet.
The entire internet. You are taking your company's most sensitive proprietary data and placing it on a public street corner.
So what's the acceptable answer?
Restricting the database ingress to accept traffic strictly from the specific security group ID attached to your internal Kubernetes worker nodes. It tests whether your default operational posture prioritizes rapid convenience or structural security.
Let's examine exercise 3, the buggy network policy. The interviewer shares a snippet of Kubernetes YAML code on the screen. The setup. You have a front-end web application trying to communicate with a back-end API service, but the traffic is timing out.
A tale as old as time.
This network policy was written to allow the traffic, but it isn't working. The interviewer says, there are 3 critical bugs in this YAML file. Find them. I want to dive into the mechanics here. If I look at the code, the policy is named allow front end, and it is applied to the web namespace where the front end pods live. Why is that wrong?
To understand the bug, you must understand how Kubernetes container network interfaces, CNI plugins like Calico or Cilium, actually enforce network rules at the kernel level.
Okay, so how do they do it?
Network policies are fundamentally evaluated and enforced at the destination node, at the point of ingress to the receiving pod. If you apply the policy to the web namespace where the traffic originates, the CNI plugin ignores it, because the rules dictate what is allowed in, not what is allowed out.
Ah, so you're putting the shield on the wrong person.
Exactly. The policy must be deployed into the API namespace, explicitly selecting the backend pods as the destination target.
That leads to the second bug, the pod selector. The buggy YAML says podselector.matchlabels.app.frontend.
Exactly the same principle. The policy is trying to apply the firewall rule to the front-end pods. It needs to apply the protective shield to the back-end pods by selecting app.backend, and then define an ingress block that allows traffic from pods labeled app.frontend.
And the third bug is the port declaration. The code attempts to allow traffic on port 80. Why is that a red flag in a back-end microservices context?
Port 80 is the standard HTTP port, typically utilized only at the very edge of the network by your public-facing load balancers or ingress controllers.
Right.
Once traffic enters a cluster, back-end application servers like a Java Spring Boot app or an Express Node.js app run as non-root users for security reasons.
Okay, and non-root users have limitations.
Yes, non-root users cannot bind to privileged ports below 1024. Therefore, backend services almost universally listen on high ports like 8080, 3000, or 9000. Specifying port 80 shows a lack of practical experience with how application runtimes actually operate inside containers.
It's an incredibly stressful exercise because you have to read the declarative syntax, not for what the developer intended it to do, but for what it will actively instruct the network kernel to enforce.
It requires a very cynical eye.
As the hour winds down, the playbook shifts us into the final phase. Segment 6, System Design and Behavioral Mastery. We zoom out from the micro-level configuration details to address massive scale and organizational leadership.
This is where you prove you can lead a team.
The system design challenge here is brilliant because it introduces a harsh real-world constraint, the setup. You need to design a comprehensive observability, stack metrics, logs, and distributed traces for a microservices architecture processing 500,000 requests per second.
That is massive throughput.
But here's the catch. The interviewer explicitly caps your operational budget at $15,000 a month.
And there's the rub.
I mean, I'd love to just propose a massive Elasticsearch cluster to handle the logs because it scales horizontally.
If you propose a direct connection from your applications into a search database like Elasticsearch at 500,000 requests per second, your ingestion pipeline will instantly collapse.
Instantly.
The sheer velocity of the data stream will overwhelm the database's indexing capabilities. The disks will redline, memory will exhaust, and the cluster will crash. To survive at that scale, an architect must introduce a robust message broker, like Apache Kafka, to act as an asynchronous shock absorber.
How does Kafka function as a shock absorber in this context?
When a massive spike of traffic hits, say, a Black Friday surge, your applications dump millions of log lines into Kafka. Kafka doesn't try to index them, it simply appends them to a highly optimized sequential disk log incredibly fast.
So it just absorbs the blow.
It buffers the massive fire hose of data. Your Logstash or Elasticsearch ingestion workers then consume those logs from Kafka at their own steady, manageable pace. It decouples the data generation from the data processing, preventing back pressure from crashing your applications.
That solves the stability issue, but we still have the budget constraint. Distributed tracing is notoriously expensive. A trace tracks a single user's request as it hops through dozens of different microservices, generating massive amounts of telemetry data.
Mountains of data.
If I try to use a managed cloud provider to store 100% of my traces at 500,000 requests a second, what happens to my $15,000 budget?
You will annihilate that budget in a matter of days. A standard approach is head-based sampling, where you randomly decide at the very beginning of a request to save 10% of all traffic.
Okay, 10% sounds reasonable.
But at 500K RPS, even 10% is an astronomical amount of data, and most of it is completely useless because it represents successful, fast requests. The playbook expects the candidate to architect a tail-based sampling strategy.
What is the mechanical difference with tail-based sampling?
In tail-based sampling, the decision to save the trace is deferred until the very end of the request lifecycle.
Oh, interesting.
You configure your tracing collectors to temporarily hold every single trace in a rapid short-term memory buffer. If the user's request completes successfully and quickly, the collector silently drops the trace. It throws it away.
You just delete it.
You only sample perhaps 0.1% of successes just to maintain a baseline metric. However, if the request encounters an HTTP 500 error, or if the latency exceeds your defined threshold, the collector flags it and saves 100% of those specific traces to permanent storage.
You stop paying to store the massive haystack, and you architect a system that only pays to store the critical needles. You let the system filter out the noise.
Exactly. It's an elegant solution to a very expensive problem.
That leads us directly into the behavioral gauntlet, because filtering out the noise is exactly what a senior engineer has to do when dealing with company politics.
Oh, yes. The hardest part of the job.
The playbook utilizes the STAR method situation: task, action, result to pierce through corporate PR speak. The first quote is brutally direct. Tell me about a time your technical decision caused a major outage or made things significantly worse.
Such a great question.
If I am sitting in an interview for a $500,000 role, my instinct is self-preservation. I want to minimize my flaws. I might try to frame a positive as a negative, like I cared too much and deployed too quickly. Or I might just claim I've never made a critical system-destroying error.
The playbook explicitly instructs the interviewer to immediately fail any candidate who claims they have never made a major mistake.
Wow, zero tolerance for that.
At the scale these companies operate, perfection is a statistical impossibility. If you say you haven't caused an outage, you are either actively lying, or your scope of responsibility has been so incredibly small that you haven't been trusted to touch anything important.
So what constitutes a passing answer?
The interviewer is testing for your integration into a blameless post-mortem culture. They want to hear you take unflinching personal accountability, but more importantly, they want to hear the structural resolution.
The structural resolution.
Yes. A strong answer is, I bypassed a testing pipeline to push an urgent hotfix, and my typo took down the primary database router for 20 minutes. I owned the mistake on the incident call, but the real failure was systemic. A single human shouldn't be able to bypass the pipeline.
So you don't just blame yourself, you blame the system that allowed you to make the mistake.
Exactly. You follow up with, so I spent the next week architecting a mandatory programmatic two-party cryptographic approval workflow for all production routing changes, ensuring my mistake could literally never be repeated by anyone else. You must demonstrate that your personal failures are converted into systemic structural improvements.
The final behavioral question targets the core reality of the SRE role: institutional friction. The interviewer asks, describe a time you had to push back on a critical product deadline because it compromised system reliability.
This happens every single week.
Right. As an infrastructure engineer, I often don't have direct managerial authority over the software developers. I can't just order the VP of product to stop shipping features. How does an engineer win that argument when the business is screaming for a new release?
You are touching on the vital skill of influencing without authority. A weak candidate will say, I constantly complain in meetings about our technical debt until the product managers finally relented.
Which is just annoying.
It's adversarial and subjective. A strong candidate uses the framework we established at the very beginning of the interview. Error budgets.
You use the math.
Exactly. You remove opinion from the battlefield. The green flag answer is, I didn't argue with the VP of product based on my feelings. I brought the objective telemetry data. I showed the leadership team that due to recent deployment instability, we had burned through 115% of our quarterly error budget. We were actively violating our customer SLAs and risking financial penalties.
It's hard to argue with hard numbers.
And you don't just say no. You propose a data-driven compromise. You say, I suggested we delay the global launch, but release the feature behind a targeted feature flag to just 2% of our internal beta users to mathematically prove its stability before risking the broader platform. You operate as an objective risk manager, utilizing data to negotiate a safe path forward.
We have survived the full 60 minutes. We have architected zero downtime migrations. We have navigated complex Kubernetes networking bugs. And we have managed the political friction of product deadlines.
We made it.
We have reached the outro of the playbook, the reverse interview. The candidate's turn to ask questions. The playbook notes that if a candidate asks no questions or asks purely transactional questions about vacation days, it is a negative signal regarding their passion for the craft. But the playbook details an ultimate mic drop question that a candidate can ask to completely flip the dynamic of the room.
This is where the candidate tests the interviewer.
The candidate looks at the interviewer and asks, what is your current P99 availability SLO across your core Tier 1 services, and what has your error budget burn rate been over the last quarter? Why is that such a lethal question?
Because it instantly reveals whether the company actually practices the rigorous discipline of site reliability engineering, or if they just rebranded their traditional reactive IT operations team with a trendy title to attract talent.
Oh, that's so good, calling their bluff.
If the interviewer stammers and says, well, we don't strictly track error budgets, we just try our best to keep the servers up, the candidate instantly knows the company is operating in a state of chaotic firefighting.
They don't walk the walk.
Exactly. By asking for the specific telemetry data, the candidate proves that they intend to hold the organization to the exact same rigorous engineering standards that the organization is using to evaluate them.
It establishes profound mutual respect. So how does the final scoring matrix actually evaluate the candidate? The playbook dictates that to achieve a strong higher rating, which equates to scoring between 100 and 130 points, a candidate cannot merely survive the technical questions. The rubric explicitly states the candidate must demonstrate proactive thinking, strategic architectural insight, and deep battle-tested production experience.
It is the fundamental difference between knowing the commands to type into a terminal and intimately understanding the cascading consequences of typing them into a live ecosystem.
We've spent this entire hour analyzing how to architect fault-tolerant systems. We've explored how to design databases that don't lock up during migrations, how to build Kubernetes clusters that actively defend themselves against resource exhaustion, and how to write decoupling mechanisms that degrade gracefully under crushing scale.
But there is a final overarching theme that emerges when you synthesize this entire FAANG playbook. As engineers, we dedicate our careers to studying how to engineer fault-tolerant systems for our computers. But the real test, the true differentiator of a principal or staff-level architect, is whether you possess the capability to engineer fault-tolerant cultures for the human beings running those systems.
Fault-tolerant cultures.
Can you architect an environment where inevitable human mistakes are treated as systemic flaws to be solved rather than personal failings to be punished? Can you build a culture where objective telemetry data always wins out over managerial hierarchy? Because at the end of the day, when the Black Friday traffic spikes and the servers start melting down, the algorithms do not panic, the human beings do. So the ultimate question this playbook is asking you isn't just about your proficiency with Terraform or Kubernetes. It's asking, are you merely maintaining code or are you architecting resilience?
Are you merely maintaining code or are you architecting resilience? We've explored a diagnostic landscape that goes far beyond printing out a broken line of YAML on a screen. It's about navigating the incredibly murky, high-stakes intersection of human behavior, massive distributed scale, and the constant threat of catastrophe. And that is exactly what it takes to pass the FAANG interview.